Hi. I'm traveling to Europe to attend the conference. Won't be here, but I still like to do the lecture by myself. I will do it using this kind of online video form. So today we're going to continue the discussion about the Fresnel and Fraunhofer diffraction, which we started on this Monday, and it's very important. So let's go through. What we kind of briefly go through what we covered on Monday. This is the topic of these lectures. So on Monday we kind of go through where is this from. So every wavefront, every point on a wavefront can be considered some kind of spherical wave, and the wave propagation in the space is through this kind of wavefront and new spherical light source generated, and then they form interference with each other and then propagate through the space. Okay, and so we talk about Fresnel approximation and Fraunhofer approximation. Okay, so kind of briefly go through what we discussed on Monday. So this is the first equation we show you on Monday, which is Huygens Fresnel principle. Okay, so this is trying to explain that in Huygens principle, the spherical wave concept is kind of correct, but it's not 100% correct. Okay, because when you derive it in a more rigorous way, that you're mixing this cosine term and also this 1 over j lambda term in the front. Okay, but the concept is quite close, which is this is showing the amplitude at this the first on your object plane. So every point in your image plane can be considered as the contribution of every point on this first object plane. Okay, that's the from the basic Huygens Fresnel principle. Now, because the form is not easy to calculate, so especially analytically, so we like to simplify it and through different kind of approximation. Okay, so the first approximation we did on Monday is by assuming, okay, this is just rewritten of this Huygens Fresnel principle. Okay, and you express the R01, which is the distance between 2 points on this two plane, using this Cartesian coordinate S, M, Y, and Z. So the first approximation we do is we call it a small angle approximation or partial approximation, or you can call it parabolic wave approximation, because when we try to expand this R01, okay, and expand it into this series form, and then we try to keep either the first term or the second term, which is 1 over 2b here. Okay, so we kind of explain that in this denominator term, which is control the amplitude of this the contribution of some certain point in the object plane, we kind of say that if the z distance is long enough, large enough, then this R1 and z, if you approximate R1 with z, the result you get is quite close to what you really have. So the problematic part is this part, which is in the phase term of the exponential term, because you have a very large number k here. And this one is kind of cosine and sine. So if you have a very small variation in RO1, and after multiplication with this large K number, then this could generate either +1. It can fluctuate very fast, so it would be good to if we can keep at least the this first order term here. Okay, that's the first approximation we have. Okay, so we expand this RO1 and express it as this these first two term here, one and first two term here. So we with that approximation, we can get to a form like this, which is converted from here to here. Okay, so this is the Fresnel diffraction integral we get. Okay, so and we kind of spend some time to explain, how good this form is when you compare with this Huygens Fresnel, original Huygens Fresnel integral. Okay, and we say that, and if you just look at it, because from this approximation here, we kind of check, if you want to keep the first term accurate, and this one need to be small enough. Okay, so we say that with that, you got to have a distance that, for example, this z need to be bigger than this term, so that this Fresnel approximation could provide good enough answer to the original integral. However, this kind of condition is very tight, and in fact, what we found is that you can actually get a very good approximation by using the Fresnel integral to calculate the true light intensity distribution after the aperture, even when the distance you want to detect is very close to the object plane. Okay, so how could that happen? This is related to the nature of this integral of this exponential term itself. Okay, so it tells us that when this x become very large, which is and that integral kind of converge very fast, which means that for the large x number, it doesn't really contribute to your final value at all. So at the end, we come to a conclusion that any point on the second plane, what's matter that in the object plane is the point light source within a certain range, a certain range which is equal to 4 square root of lambda pi in that kind of square. Only the point within this square can contribute significantly to the point in the image plane here. Okay, and this range actually it depends on the relative distance of these two image planes. So if your image plane is moved to a location much closer than the object plane, so this actually can be shrunk to very, very small. Okay, so to an extreme, if z is being shrunk to nearly 0, actually you are approaching this geometrical optics limitation. Okay, which is this point, the light intensity in this point is only contributed by the same light point in the same corresponding location. Okay, so it's a one-to-one mapping situation. And we kind of not satisfied with Fresnel diffraction integral. We know it could be quite accurate, but it's still not that easy to calculate. So we want to do further simplification. And so what we do is that this is the Fresnel diffraction integral. Okay, so this term we want to further simplify it. So what we do is that we expand this. Okay, we times it out. We expand it so that you have this square s square y square term, which is nothing related to this eta and zeta and eta here, so it can be moved out. Okay, in this inside the integral, you have this zeta and eta term here, and you have this cross term, which is x times 2x times the zeta term. Okay, so the approximation we want to make here is that to try to, if your distance that you observe the pattern is very far, which is z is very large, this term can actually become 0, okay, which is z need to be bigger than, a lot bigger than this. So if this becomes 0, then you can get a very nice a form which is look like this. Okay, so if you look at the right hand side, this right hand side, this integral is exactly the Fourier transform of the u function u. It's exactly the Fourier function transform of this function u here. Okay, and it's two-dimensional, and you can have these two terms. You can look at it is 2 pi f here, or 2 pi the v frequency in the x dimension, and this is the frequency in the y dimension here. Okay, so you can so you compare it with this Fourier transform. This is the Fourier transform. Okay, so that v is the frequency component. Okay, so this is what we discussed last time. Okay, so in front of the integral, you have this phase term. Okay, but if what we care is the intensity, so when you calculate intensity, it's kind of, you need to times complex times this amplitude with its complex conjugate, and this phase term will all go or be cancelled out, become 1. Okay, so this phase term, it doesn't matter what it is, and we want to calculate intensity. If what you care is intensity, this doesn't really matter at all. So at the end, the intensity distribution is kind of it's a square of this Fourier transform of that u function. Okay, so this is the Fraunhofer diffraction pattern. So if in the case, if you have a square pattern there, you shine a light which is plane wave, shine and let it go through this aperture. This is what the diffraction pattern that you are going to detect at a distance pretty far away. That's called Fraunhofer diffraction pattern, right? Now, how far you are talking about? So you say, so this term, if you want to make that much smaller than z, okay, because k is very big. So if you have, let's say you have aperture width, okay, because this zeta and eta is the size of the object. Okay, so if you have a width of 2.5, which means that your zeta and eta is 2.5 centimeter, and after it times it with a very large k factor here, actually you can end up with a distance super long. Okay, so if you want to, in the free space, if you want to observe the Fraunhofer diffraction pattern, you got to go at a distance pretty far away. So this is a 2.5 centimeter pattern. Okay, pattern. So in many applications, this may not be practical. Okay, this may not be practical. Okay, but anyway, that's what we get. Okay, so inside this region is a parabolic approximation region, which is you have a spherical wave generated here. Okay, so you have at some certain distance you can approximate the wavefront with a parabolic function. When you get to very far away, and then the wavefront become very straight, so it's kind of a plane wave. Okay, this is the the comparison of the Fresnel diffraction pattern and Fraunhofer diffraction pattern after an object. So let's say you have an aperture which has opening which is have a 2a, the opening have a width of 2a, okay, and then you have a plane wave that come in from this side, and after that you start to generate diffraction pattern, and if you check, you put a detector image sensor here, you detect the image, and this is the pattern you are going to find. Okay, so this represents the original structure and ideal transmission right after this aperture. Now, after you propagate some very short distance, you will start to see that your pattern start to change. Okay, but still having a shape very similar to the original pattern, which is very sharp edge. But when you start to propagate in the space, you will see that the pattern, optical pattern, keep changing. Okay, keep changing, and until after some certain distance, that you will see that the pattern start to fix. The pattern start to get fixed. But when you keep going up, the pattern remain the same, but the size of the pattern will become larger and larger and larger. Okay, so when you see this pattern start to fix, that means that it go to the Fraunhofer diffraction regime. Okay, anything before that, from the right behind the aperture to all the way before that happened, that's domain belong to the Fresnel diffraction domain. Okay, so you can actually define a number called Fresnel number to describe and this situation. Okay, this Fresnel number is defined by d squared. In this case, d is equal to 2a here, and d squared over lambda z. Okay, so which means that if you have a very large aperture, okay, you have very large aperture, and the larger the number, the closer the pattern to this original pattern. Okay, so when the distance start to increase, this Fresnel number start to decrease. Okay, like for example, in this case, that NF number is 0.1. Okay, further propagate away, and the NF number will be smaller and smaller. Okay, so which means that smaller Fresnel number, you will see the Fraunhofer diffraction pattern. Okay. Now there's another way to explain this kind of pattern change behavior. Okay, which is we're going to cover it soon later. But I just pointed out here. So we keep emphasizing that whenever you have a pattern on this aperture, you can think of it as a superposition of a plane wave propagating in different direction, and then they form interference on this pattern and to generate this kind of pattern you have. After they leave this plane, different plane waves start to propagate different direction. Okay, so when they propagate to a distance pretty far away, you can think of it like each plane wave, they are kind of separated far enough. Okay, so they do not overlap with each other too much when you propagate to a very distant, very far away. Okay, so that's why what you're going to see is that intensity will keep dropping, but the pattern remain the same because they stop interference with each other. But at the location pretty close to the aperture, the plane wave propagating in different direction, they're still having a significant overlap in this near field region. Okay, so then and when they propagate, because a different plane wave when they propagate, they have different kind of they have introduced different kind of phase delay in different directions. So then when they do superposition together, your pattern will keep changing. Okay, it keep changing because you still have this plane wave at different direction. They are having significant overlap. Okay. So that's related to the next topic that we want to talk about. Okay, so which is a different view of looking at this the image and this we analyze these spatial frequency of whatever image you have. Okay, so the idea is that any image you have on a 2D plane, okay, you can think of it as a superposition of the a pattern with different kind of spatial frequency and spatial frequency on this plane. And you can think of it as a superposition of different kind of plane wave on that plane. Okay. So this is a Fourier transform. Okay, I just simply put it here to remind you what's Fourier transform. Okay, so every function you have, this is 1D. Okay, if you have 2D, you just f of x and y. Okay, this is 1D. 1D is that you have different kind of elementary function, and f of v, which is the Fourier component of each frequency, and which is the amplitude of each elementary function. So every function, you can think of it as superposition of the elementary function. Okay, this is just how you get this. The Fourier transform. Fourier transform is a way to get the amplitude of different elementary function, which is cosine function here. Okay. Let me remind you, everything we talk about so far, we are talking about one single frequency. We are talking about monochromatic light. Okay, you only have one single omega. Okay, which means you only have one single wavelength. Okay, so now how do you create? How do you generate a plane wave with only one single frequency on a plane? Is simply by let me draw it. Simply by having the light wave propagate at different direction. Okay, having the light wave propagate at different direction. So if you have a plane, okay, we may not. I may not need to draw it. Okay, because next slide we will show that result. Okay, so this is the slide actually can explain the relationship between a plane wave with certain wavelengths. Okay, so how do you generate using the same frequency of light and only one single frequency of light, and how do you generate different kind of spatial frequency on a plane? Okay, it's pretty simple, which is it's done by having the plane wave tilted at different angle. Okay, different angle. So you can think of it that different spatial frequency is actually represented by the same plane wave, but same color of light, a plane wave that tilted at different angle. Okay, tilted at different angle. Okay, so here, let's say if you have a wave that can express in the SYZ in this way. Okay, you have amplitude, and it has its phase term, J, KX, X, KYY, KZZ. Okay, so if you are having some certain spatial frequency, for example, in this plane, okay, and by knowing for example, knowing the frequency of Ks and Ky, you can actually calculate what's the Kz in this Z direction, right? So because Kz squared plus Ky squared plus Kz squared need to be equal to K, okay, which is K equal to 2 pi over lambda. Lambda is the wavelength of the light that you use. All right. So if you want to calculate kz, it can be you can take in the square root of this, so it could be k squared minus ks squared minus ky squared, taking the square root. That's how you get this kz, right? Kz. Now, how do you calculate ks? Which is simply using this simple sine function here. Let's say this is the k have the k you have. If you want to see how much what's the ks in this x direction, then it's a k times this sine theta x, which is in this part, okay, which is this. And ky the same thing, okay, ky the same thing here. You have the theta y projection, okay. All right, so you know, the way to look at any image in a space and in any image plane, any object plane, you can think of it like you have plane wave come in, and because you have some kind of structures on this plane, okay, so after you transmit it, after the plane wave transmitted, you will create some kind of light pattern on this plane. And this light pattern, you can think of it as a superposition of different kind of the plane wave propagating in different direction, all right? And each direction, it represents a different spatial frequency on this xy plane. Okay, and then the intensity that propagate at different direction representing what? Represent the amplitude of that spatial frequency. Okay, so if you explain it from the Fourier transform point of view, amplitude, which means Fourier transform is trying to extract the amplitude represented at different plane wave propagating in different direction. Okay, that's the way we look at it. Okay, so if you having you want to detect the image right after the aperture here, you can see this plane wave, they're still having a significant overlap. Okay, significant overlap. When they propagate pretty far away, this plane wave kind of, okay, they do not overlap. So that's why your pattern start to become more stable. There's a Fraunhofer diffraction pattern, okay, and different plane wave depends on the amplitude you have. It will show you the intensity pretty far away. So that's Fraunhofer diffraction pattern. Fraunhofer diffraction pattern. This slide, what we want to show you is that how the harmonic function or plane wave, when they propagate in space, how do we understand it? Let's say in some you have a u function which is representing the amplitude. Let's say in a location equal to z equal to 0. Okay, so that in that z equal to 0 plane, you detect your optical field has this kind of expression, which is simply a plane wave expression. Okay, plane wave expression with the spatial frequency ks, and in the x direction ks, in the y direction ky. Okay, and then when this plane wave propagate over a distance z, then this new amplitude, this new amplitude distribution become this function times its exponential jkz. Okay, this is simply just a way to rewrite the previous function we have. Okay, so this is the function we have. Okay, this is the function we have, and we look at it as the this function. You can consider it as the from a plane wave, which is at z equal to 0 location, you have plane wave that can be described like this, okay, in the x and y. This plane wave can be described like this. So after this plane wave propagates through in the space with a distance z, and this is the final complex amplitude that you will have. Okay, you will have. And from this expression, you can know that different amplitude, I mean different spatial frequency of light on this xy plane. Okay, they actually have different kz value here. Kz value here. Okay, so which means that different plane wave, when they propagate in the space, they actually experience different kind of phase change. Okay, different kind of phase change. Okay, so the way we look at how look at the free space propagation of different plane wave is like for an image for input plane here, you say it's f x and y. Okay, so you can decompose them to be a superposition of plane wave propagated at different direction, and in a different direction may have different amplitude. Okay, so you have this kind of main function kind of decouple them. Okay, and every plane wave propagate in different direction. When they propagate through a space, let's say a distance z here, z equal to d here, and what they do is that different plane wave, they go through different kind of phase change here. How much phase change each plane wave experience is simply can be calculated by this. Okay, so if your ks and ky is big, okay, then your kz value will be small. Okay, if on the other hand, if is that there's no ks and no the ks ky equal to 0, which is a wave that is propagating in this direction, okay, then in the x direction you can have very large kz wave number there. Okay, so the way you look at this, how image, what's the relationship between the image here and image here is that for image here, you can decompose them into different kind of plane wave and their superposition. And when this plane wave propagate through a space, let's say z equal to d, then each plane wave goes through different kind of phase, having an extra phase term. Okay, by including that, considering the extra phase term, and then you do some kind of superposition of this new transform function here, and then you can convert it back to this to calculate the true intensity pattern. Okay, so let me So this is the way it works. Okay, so in the first image plane, you have the function f, x, and y. Okay, and then you do you check it through its elementary function and do Fourier transform. Okay, and you know that on a different component and what's the amplitude you have. Okay, and when you propagate in the free space at the distance z, okay, and each component they have extra phase term to add into this your Fourier transform function, okay, and then you do inverse Fourier transform of this entire function here to get you here. Okay, so this is the Fourier transform of this f of x and y function here, okay, to get this component. And when you propagate in free space, each component depends on the spatial frequency you have, and you have different kz. And then after propagating the free space after z distance, and you can get this a new Fourier transform here, okay, and then you can back calculate this based on this new Fourier transform to construct the new function that you see in this plane. Okay, so let's see. It's kind of saying that it's a free space propagation of light is kind of a Fourier transform process. So this slide is pretty much just what we talk about. Okay, so in the first plane you have a function f of x and y, and then is equivalent to you can think of it as a superposition of the elementary function with different kind of weighting factor, which is and can be find out by Fourier transform. And then when these waves propagate in the free space, okay, and each component kind of experience an extra phase delay term here, okay. So based on this new phase Fourier transform, and then you do this is the inverse Fourier transform. No, it's not inverse. So this is the Fourier component with this extra phase term, and then do superposition, and then you can get the new s and y and z. Okay, so this is the how we look at the free space propagation of light image here. The next topic is kind of trying to explain why we will have optical image these by using this periodic wave to synthesize this object image. There is some limitation. Okay, there is some limitation. Okay, so so any object, let's say we can decompose them into superposition of different plane wave, right? But the spatial frequency of this plane wave will be limited. So based on the wavelengths of light that you use, kx, ky, it cannot be bigger than k, right? Cannot be bigger than k. What if you have a feature that has very fine pattern? Actually, to construct that, you need a spatial frequency which is pretty large. Okay, so what happens if you just use a light that doesn't have such a high spatial frequency to illuminate this pattern? Okay, where does this high frequency component go? Okay, so this is to show you that if you have object that has a very fine high resolution patterns, okay, and that will require a spatial frequency larger than k vector to reconstruct. And what happened to those patterns? Okay, so and because that k vector, if this one is bigger than k, which means that your kz is here, right? So if an object, it has some very high spatial frequency that bigger than k, and this will actually become an imaginary number, right? Imaginary number. So when this wave, a high frequency wave, propagate, what happens is that instead of a propagating wave, what you're going to have is you have a decaying wave. You have a decay. This is a evanescent wave. Okay, this is a evanescent wave. It's kind of different from the total internal reflection. Okay, so you have an emission wave, so which means that this high frequency component, okay, the information, this high frequency information do not propagate at all, okay, because only plane wave with spatial frequency smaller than k, they will be allowed to be supported in the free space to propagate. So any frequency higher than k, those will only exist in a location very close to your object plane, okay, and then it will quickly decay, okay, so you won't be able to observe it in the pretty far field away because those wave doesn't propagate, okay, doesn't propagate. But there are some device that people or image approach that people can make, and for example, some people can use some kind of a plasmonic device so that it can enhance the near field pattern so that this distance can be extend to a longer distance so that they can detect it, okay, but it's still very small, very short distance, okay. So this is explain, why when you do optical image, okay, normally we do far field imaging, and in far field imaging you won't be able to see any optical feature with the size and smaller than the wavelengths of light, okay, because those information do not propagate, it just disappear at a distance very close to the object, okay. You won't be able to collect those propagation information, okay. So